Oh yeah. Can you hear me? Okay. Thank you. Okay, so thank you very much to the organizers for giving me the opportunity to speak here. It's a lovely place and a lovely conference. Thank you very much. Yes, so the Higgs and other thorns in the side of the swampland. I want to play the devil's advocate and try to see whether we can challenge some of the claims of the swampland by counterexamples, by problems with phenomenology and so on. I think even though we all, of course, like the swampland idea, that is also important and has to be done. So I basically will have two topics based on recent work with Fredrik Denneff and Tim Vrase, who is here, and work in progress with Daniel Junghans, Aaron Palti, who is also here and gave a talk, and Andreas Schachner in Heidelberg. So the first topic is the de Sitter-Swampland conjecture, the Higgs potential, and related issues, and the second is the Swampland distance conjecture and axionic field ranges, which is also related with the gravity conjecture. Okay, so let me start. Let me start very generally. So string compactifications to 4D produce a flux-induced very large landscape. I think we all agree with that. And the simplest solutions are, of course, Zusi-Minkowski or ADS. And now, in my opinion, there is strong, I am willing to sacrifice the word strong, not to disagree with what Thomas van Riet said, for metastable de Sitter vacuum. Of course, how strong or whether it is strong is a matter of debate. Now, clearly it is important to keep questioning the constructions leading to this de Sitter or metastable de Sitter and scrutinize the evidence. And in this context, it is, of course, extremely interesting that recently a stronger version of these doubts concerning de Sitter has been put forward. I refer to this as a V prime over V conjecture. And what is intriguing about this is that one would have thought it clashes with cosmology right away because the universe expands in accelerated fashion, and that turns out not to be true. Indeed, a simple quintessence model with a potential e to the c phi and an order 1 coefficient can satisfy the conjecture and replace lambda. That, of course, is at first sight extremely interesting. I'm sorry I have no time to do justice to all the relevant papers, and many of the authors are here, so I apologize for this. Let me turn right away to a problem that one might have with this V prime over V conjecture. So, in the presence of the standard model, such a quintessence term is simply not sufficient to save the conjecture. Namely, we also have the Higgs potential in the simplest form, kind of simplified, oversimplified. It is h squared minus q squared squared. And this famous Mexican head potential, of course, has the feature that we live here in the minimum, and according to the quintessence setting, we, in addition to being here, roll along a very flat trajectory, very close to zero. Now, but clearly, this potential violates the conjecture at h equals v. Namely, here on top, we are much higher up, the energy is much bigger, but the rolling is equally flat as it is here. And so this ratio v prime over v becomes tiny and not order 1. On second thought, of course, there's an immediate and obvious remedy to this. One simply multiplies this factor e to the c phi, not just with lambda cosmological, but with the whole potential, including the Higgs potential. That means that if I go higher up due to this term, then still the exponent always has this feature of the ratio v prime over v being this coefficient c. If that's order 1, we are still fine. Okay, so at that level, things look good. But then a further problem is encountered. Namely, in this setting, it is not just quintessence. It's actually what is known as coupled or interacting quintessence. And that involves an extreme fine-tuning of many operators. And the simplest way to see that is if you have this very light scalar, there's nothing wrong with that. There's a shift symmetry protecting it, basically. The potential breaks the shift symmetry very weakly. Now, once you couple it, here in this term, there's no tiny number like here, and loops immediately drive all the operators up, and this has been noted in our paper in a limited way and recently analyzed very nicely and clearly this paper by Marsh. And so that's an issue. But let me for the moment accept this tuning issue, although I have a hard time, to be very, very honest, personally, as an effective field theorist. Let me accept it and check other constraints, fifth force constraints, which are also an issue because based on the equivalence principle, or the equivalence principle is violated by diagrams like the one shown here. So let me check my time. I'm not going too slow. No, it's okay. Yeah, you had time to read this diagram. This is my quintessence field. Due to this coupling to the Higgs potential, there's no mixing with the Higgs. So this is one of the tunings. I have to enforce there's no mixing with the Higgs. But there's, of course, a coupling to h squared. So this coupling induces such a loop. And this loop can, via two Z lines, be connected to a quark line. And the quark is part of the proton. And then furthermore, somewhere here, there has to be, or I can put in a mass insertion for the quark, which will lead to a different coupling to neutron and proton because they are up-type and down-type quarks and they have slightly different masses. So it's clear from this how to estimate, at least very roughly, how the equivalence principle of materials with different numbers of protons versus neutrons are violated. And this field here is really massless. So it's a long-range force and can clearly be tested. Adelberger and company are doing this, I think, in the world, in a leading way in the world. And so we find significant but not yet critical constraints. We are missing very roughly a factor of 10 to the 4 to actually rule out the model in that way. But this has been improved. So recently, nuclear binding energy effects and diagrams like this have been considered, and our bound has been strengthened. I shy away from quoting the detailed numbers, but it comes about to almost kind of rule out C equals 1. And the reason why you can, with this diagram, also violate the equivalence principle is interesting. I mean, this naively couples only to gluons. That's why this effect is larger. And the gluons, of course, couple to the quark, but the gluons do not distinguish between up and down type quarks. So you would think, okay, it's a fifth force, a tiny extra fifth force, much smaller than gravity. How will you ever see that? But the interesting point is that different nuclei have different contribution of nucleon binding energy to their total mass. And so coupling to gluons is not harmless. The coupling to gluon actually distinguishes different materials based on what nuclei they contain. And so, according to these authors, the effect is stronger. Furthermore, as we also pointed out, but one may consider the maximum at the perturbative vacuum of QCD before chiral symmetry breaking. Now that sounds at first sight a bit crazy, but I think it is not. I mean, our world is, of course, in confinement and chiral symmetry breaking. But if I were to compactify our world, our 4D world, on a tiny torus, we all agree confinement will go away, would it be perturbative QCD vacuum? Okay. So now let's decompactify suddenly and see what happens. Well, we will roll down to a lower vacuum with confinement and chiral symmetry breaking. So before we were up of some potential. That is now very hard to somehow shield and couple to any quintessence field, right? Because this is coupled to everything very strongly. So this is kind of vague because, you know, who knows this perturbative point very well. But this point has also been strengthened and made more quantitative by considering the potential in the pion sector, again by the same authors. Oops, sorry. Now you can do a slightly less crazy thing. Let's not go on top of the potential where confinement is, where so to speak, where we are deconfined. But let's just go a little bit up the pion trajectory in the space of chiral symmetry breaking situations, you know, kind of along the Goldstone directions, okay? But there's a potential. The pion is massive. The potential has to have a maximum. And according to the estimate of these authors, this already now is kind of very hard to avoid. They don't say cannot be avoided, but close to that. And the naive bounds are C to the 10 to the minus 2. So things are getting difficult. Now, let me return to the Higgs and try to solve the problem by introducing a further non-quintessence scalar. This is something Fernando just already mentioned. namely replace this situation by such a situation. So forget about the quintessence, and let's try to an extra chi equal to the Higgs to get rid of this maximum of the Mexican head. Naively, this should be possible. And we have argued, and we argue that this is fundamentally difficult due to an interesting feature of this potential, namely the feature that you have then unavoidable saddle points. It's very easy to see. This is my Higgs potential here on this dimension. In this direction, the extra field. So we are here, and I have an extra scalar, and this is supposed to be a minimum, such that we don't have extra massless stuff around. However, if I stay at the point where the Higgs, where the electroweak symmetry is unbroken, then of course it's always a maximum or a critical point in that direction. But we could remove the maximum by having the extra scalar having a slope here. Now I can go down here, and at some point I either have a runaway or a maximum or minimum above 0. Then I violate the conjecture, or I at some point go to or below 0 here. If I have the extremum below 0, there's no problem, right? And V prime over V conjecture doesn't say anything about critical points below 0. So now I have a critical point here, a minimum here, and a minimum here. Now there is, however, there must be by continuity some line, some path in field space connecting them. And since this is a minimum, it has to go up, and then it has to go down again. And there is no way you can do that without having on the way a saddle point. And that saddle point will most naively be above 0 and violate the conjecture. And now, of course, there's a very fine way out, namely you can be here below 0 due to the quintessence field. You can make this very, very close to 0. I think there's a tiny way to somehow still get around it by having milli-EV type potentials, but naively, this is pretty deadly for any kind of particle physics motivated model building. It's a topological issue. So, okay, so this issue of designing suitable potentials, VH of H chi, has recently been discussed in more detail, and in particular in the very nice paper by Ciccoli et al. that Fernando just talked about. And he didn't do justice to their detailed analysis, and they play exactly this game and show how to avoid our previous no-go theorem, roughly speaking, by cutting the chi field space appropriately. I mean, it could just be that the dangerous saddles I was talking about are somehow too far away. On the other hand, dismissing this option, this no-go theorem that I just tried to sketch has actually been, I mean, in our paper it is just a comment of one paragraph. It has been promoted to an actual no-go theorem in this paper by Murayama, Yamazaki, and Yanagida. So the summary for me of this is that in any case, VH of H and chi with massive chi appears not to provide at least an easy way out. I'm not saying it doesn't provide a way out. Good, that brings me to something that I would like to call an intermediate summary, because I still have another topic to discuss. Am I about half? Yeah. Okay, very good. So, intermediate summary. So, I think that the V prime of V conjecture might, I'm not saying it does, but it might fall on simply phenomenological grounds. A logical possibility would then be that the conjecture may still hold in string theory, which hence does not describe the real world, and I do not hope that. However, critical points at V larger than 0 may exist even in string theory, and of course there has been much work on this, I mean, many years ago until recently, and I want to review this. I think actually Tim will probably talk about this. Tim Brase, sorry. And I will only recall a recent, very simple example, which already Fernando mentioned, but I want to show you more explicitly, because I think it's a very nice paper and very nice, simple idea. So you can tune the alpha prime corrections, or you can choose a Calabi-Yau with alpha prime corrections such that you have a positive runaway at large volume. And then it is very easy to argue KKLT type without any uplift, just by interplay of Gugino condensates, that you have some structure, some minimum here. As soon as you have that, by continuity, you have a de Sitter maximum. And for me, this is pretty convincing that we are not in this horrible red line here that which is true and the world is not described by string theory. Okay, continued. So one may now say that the conjecture is really about forbidding metastable de Sitter and sacrifice V prime over V. Okay, that is still, of course, a very interesting and important conjecture. But of course, this puts us back to square one, namely that the old debate about KKLT, LVS, etc., being controlled, calculating corrections, and so on. And such a critical debate is, of course, needed. But at this time, I do not see strong new reasons that the de Sitter landscape must fall. In no way do I say that I know the opposite. Okay. What I would say the new discussion, however, shows is not that the de Sitter landscape has to fall, but it shows you an interesting kind of counter-argument. Namely, that the de Sitter maximum of the Higgs potential suggests that string theory has a way of realizing semi-classical de Sitter solutions. And that is a very obvious thing. I mean, you take our standard model, you put yourself on top of the Higgs potential, right? And clearly we are not stable there. You roll down, you cannot have inflation there, of course. But it is classically a solution. So somehow string theory does this, and no-go theorems have to take that into account. As I said, I'm not arguing against the difficulties that people see and that may be true in KKLT, etc. Good. I change topics. I want to discuss another issue, which is maybe not as hot at the moment, but I think also important. And I want to remind you that apart from the de Sitter swampland, of course, a key phenomenological reason for thinking about the swampland is inflation. And key constraints here come from the gravity conjecture for axions and from the swampland distance conjecture. I heard that there was already a very interesting talk by Matt Kleban this morning. I'm sorry I missed that. So maybe I will overlap. I'm sure he also introduced to you the idea of KNP. Let me nevertheless start here. Okay, so field ranges inflation. We all know the gravity conjecture states m smaller than g m Planck for the lightest charged particle. We all know this translates for axions to a bound on the action of the instanton, and that forbids Transplanckian F values with very important caveats, which I do not now review. A loophole is to realize only effective Transplanckian axion. And this is a famous Kim-Nilles-Pelosi or KNP model. You have two axions. You somehow manage to put yourself on a winding trajectory. Sorry, don't fall asleep. New things will come. I have to start slowly, okay? I heard somebody snoring. I apologize. And I agree, but I do not know how to start without saying that. So again, this picture, and now concretely, how to put yourself on this trajectory is also fairly easy. Namely, one can implement this using, I would call it three-form Higgsing a la Dvali. Or we call it winding inflation in our paper on this. So namely, you take two axions and you give a certain linear combination of them a potential. So here I wrote down the dual version where -1 form and 0 form are brought together by Higgsing. Of course, a dual version, as Dvali wrote it first down, is a 2 form and a 3 form brought together by Higgsing. Okay. So this is a very natural thing to do also in string theory. And it realizes this by simply removing the orthogonal direction to this red line, if you wish. Okay. So concretely, how do you do that in string theory? Let's go to large complex structure. Here are the complex structure moduli, Z1 to Zn and U and V. U and V are distinguished for reasons to become clear in a second. Let us go to a large complex structure limit, at least for these moduli. So imaginary part of U and imaginary part of V are much bigger than 1. So now the Kähler potential takes this shift symmetric form. You see right away, and the real part here. Sorry, I'm talking on. No, it's okay. Okay, that's right. So the imaginary part is the Axion, a large Axion vest such that I'm a large complex structure. Okay, so to be sure, here the Axion has dropped out. But of course, this structure is corrected by exponential terms, which are small because this axion is the imaginary part here. Same thing for W, and in W I have the choice to have such a linear combination of U and V. This is possible up to exponential terms because the periods at large complex structure of the Calabi-Yau have a simple algebraic structure. This is not something ridiculous. It's not a ridiculous assumption to have only these linear terms here by some flux choice. So without exponential terms, it is now clear that the W leaves one original shift symmetry between real U and real V flat. If n is much bigger than 1, this direction is closely aligned with the real axis, and the exponentials induce cosine potential terms for this light field, cosines with different periodicities. Yeah, so we are still here. This is now very closely aligned, and I wind. So disclaimer, I will not have time for inflation phenom and for the famous mild pre-gravity conjecture loophole, which is related to this. Oh, sorry to call for him name, I apologize. I will also not discuss other interesting work using complex structure moduli to enhance field ranges. Many of the authors are here. Many of the authors are in fact locals in Madrid. I apologize for not having time. I want to tell you what the new twist is that in this paper with Aaron, which I advertised at the beginning, we are going to make. 10 minutes? Yeah. Good. So justified and very inspiring criticism of the previous proposal has in fact been raised by Aaron Palti. I forgot, actually also in Palti and Claver, there are several papers discussing this. And indeed, the following problem arises. If you choose this flux number n large, you may affect the stabilization of the Axions. Sorry, this is a typo. This is imaginary U and imaginary V. So the Axions can be stabilized at the wrong ratio, such that a large F is prevented. And in fact, we show that in a simplest setting, this is deadly. Actually, Aaron is right. So the simplest settings, really, this problem is very serious. So we are still in the process of analyzing whether large field inflation is still possible using some more complicated, for example, 3 moduli, mixing, etc. But crucially, for this talk, the crucial new point is that if I don't care about inflation for the moment, but just about large field ranges, because I'm talking about what the Swampland constraints are, the situation actually looks very promising for the following reason. One can get around this issue by considering what we would want to call a misaligned winding trajectory. Indeed, you can constrain the axion to roll in a trajectory which is not a diagonal, but just a little bit off, by the same 1 over n factor that you had here in this aligned winding trajectory. You will still, after a certain number of revolutions, come back to the same trajectory, so it will close on itself. It will still be roughly n-fold enhanced. But note, you are now on some arbitrary direction, for example, the diagonal, almost a diagonal, on this torus. Now that has crucial implications, because the flux realization of this, I again show you the misaligned and the aligned version, the flux realization of this is such that here you have 2 flux numbers which are large and comparable, and here you have a hierarchy in flux numbers. If you look at the stabilization of the corresponding axions due to F terms, you see that the ratio of the derivatives of the scalar potential here and here is very different. Here it can be order 1, here it's always hierarchical. This hierarchy is the issue that drives us into a regime where the axion decay constant cannot become large. Here, this problem is not there. Misalignment allows us to be at a generic point in terms of moduli and modular derivatives in moduli space and still have extended F. And so one can be very optimistic that maybe not inflation, but a large field range can be realized. So this brings me already to transparency 1 of the summary. I think, oh, you only have the 5. Perfect. Not even yet. Okay, good. I'm rushing too much. Okay, very, very good. So you have time for questions. No problem. So what do we conclude from this? I'm now talking about the conclusions for the second part of the talk. Yeah, fine. The second part of the talk has the following conclusions. It appears possible, I personally would say even likely, I'm not sure everybody would, even of course agrees, that large axionic field ranges can be realized with full modular stabilization. So this to me is kind of a violation of what I would think of as a general expectation from the Swampland. However, one should be careful, it is not in conflict with the actual Swampland distance conjecture for modular spaces, as we in fact pointed out in the paper, because one thing is modular spaces, and another thing is once you stabilize as axions, break supersymmetry, and have some flat axionic potential. So there, I think it is conceivable that we break this and do not clash with the, I think, very kind of mathematical and elegant and consistent Oguri-Waffer Swampland conjecture in the supersymmetric case. So I hope that this could be an outcome. It would, however, be in conflict with a possible non-Zusi generalization of this conjecture to effective field theories with very light scalars. That is kind of would be the positive outcome if this can be established. Now, large field inflation would, in this approach, not yet be established. As I said, the potential is maybe not suitable in this case. In fact, both cosine terms, the oscillations on this large field range, have short periods, and it does not look possible immediately to do inflation. We are working towards this, and I would not have a definite expectation at the moment whether the outcome for inflation, large field inflation, would actually be positive. But in effective field theory, it's still interesting to maybe construct large F axions. Now, let me come back to the first part of my talk and try to summarize that also. So it is very interesting, I think, to explore some logical, for example, Higgs or other consequences of the V prime over V conjecture. And based both on the developing equivalence principle violation constraints and the required tuning, I personally am skeptical, but of course there can be surprises. Now, independently of the V prime over V conjecture, I find it also interesting to imagine that we are living in a non-fully stabilized compactification. Okay, that is, of course, something that is kind of behind that and a fallback option, which is still interesting. But the observed Zusi breaking energy can, as far as I know, presumably not be allowed to drive the rolling of modulus. As far as I understand, in all the models I looked at, I can imagine the effect would simply be too strong. I mean, we would roll too fast in terms of how much the Higgs coupling and other things change, or the Higgs mass as we roll. But this is a question for discussion. I'm not saying that this is something I have no theorem, no deep knowledge of this. If so, I do not see why an extra very flat scalar would help. How does this extra scalar overcome the problems of getting approximate Minkowski with strong Zusi breaking? So kind of behind my concerns here is the fact that I would like, before I talk about quintessence, to see how I get Zusi breaking and how I ensure that Zusi breaking does not drive the modulus to which it unavoidably couples in supergravity to decompactification or in any other, large field regime. So these two are, honest questions which I would hope maybe somebody would stand up and answer. Thank you very much.
Yeah, good one.
Thanks for the nice talk, Arthur. So you mentioned possible loopholes in this unstable de Sitter counterexamples, various possible ones on various issues with them. But you also mentioned that if we say the conjecture is restricted to the unstable, to the stable ones, we lose everything. But I don't understand what you mean by that, because you can say it applies only to regimes where there's a Hessian is positive and V prime over V is bigger than constant. So what is the statement about that?
Sorry, I didn't understand. Which point do you mean? You have here, you mean this transparency?
There was a transparency where you were saying that if we say that the unstable ones are not allowed, we fall back to no use.
Yes. Oh, okay, very good. Yes, sorry.
You're not sacrificing V prime over V. You're just saying that it applies only to regions where the Hessian is positive. You're making a too strong a statement.
Let me see.
Right there.
Right
the
there.
First sentence. What do you mean by sacrifice?
No. This is a different story. So this statement is that one option that I think is logically possible. I mean, forget about v prime over v and simply say, okay, I see what you say. Okay, okay, good. Yeah, there are three options. You're right. There are three options. Okay, so the first option is v prime over v, which is still not fully ruled out, but in trouble. There's the other extreme option, just metastable de Sitter, which is what I discuss here. And I agree with you that there's another option, which is v prime over v holds in situations when the second derivatives are positive. Okay, that is what. Sorry, I didn't emphasize this. It's important.
I guess you weren't in the morning, but there's evidence that that actually is needed for some of the arguments. That's the condition. So there's indirect evidence. There's a weak coupling regime where you can show that that is necessary to make it argument. So that's not just a random statement.
I'm happy to believe that and to consider that further. The possible problem or question I have with this is that even if I'm in an unstable regime, which would then be allowed, right? I still have a solution, right? Classically, I have a solution. So so this solution is, I mean, if I can have a solution which is unstable with the sitter, then it seems to be a conspiracy that somehow then the same solution cannot exist with positive energy. I mean, it seems to me that the key point is having a solution.
In the argument, I guess you were in the morning, so I explained it. In that context, when when Eran talked about it and also I talked about it, the de Sitter entropy will not apply if you have too much curvature negative down. The de Sitter entropy was crucial to connect the de Sitter distance conjecture with the.
I see. Okay.
So there's actually good reason that might be necessary. So it's a simple refinement of the conjecture rather than losing everything. Okay,
very good. Thank you. I'm sorry, indeed I wasn't there, and it seems like so you're saying de Sitter has to be kind of long-lived enough. Such that you can count its entropy, right?
If it's sloped this way, then you're in trouble.
Then you can't live long enough to count the entropy and can't apply this argument. Okay, very good. I understand. Okay, nothing to say.
I have a comment on Joe Conlon's paper, and it relates, I think, to your argument about the saddle points.
Okay.
In all this Swampland discussion, we're actually talking about low energy. I mean, we should be talking about low energy effective theories,
right.
Which means there should be a cutoff scale. And so I'm wondering, I think on this picture, the de Sitter maximum, we have no control about at what energy it is or how high it is. And so it could very well be that the potential just blows up basically and is cut at the cutoff scale.
You mean that this point, which I dashed, is too high to trust the theory there?
Exactly.
I agree, and I'm sorry, this was only for reasons of time. I agree that there is a loophole in this. Right. Namely, you need to make somehow this minimum come in early enough, at large enough t, so that you can still trust this. And naively, if you trust, say, KKLT step 1, W0 fine-tuned, this can be achieved. But it is also a valid criticism to dismiss already this first step of KKLT. So then, of course, it could be that this just goes up, and any further minima are in a stringy regime. I see the logical possibility. For me, it's still a very interesting argument. Okay, I'm not saying more than that.
Just to comment further on your argument about the saddle point, or
yes,
in your context.
Let me go to saddle points. I think that's an important point too.
Do you have any control on precisely how high this saddle point maximum would be, basically?
Very good. Yeah.
So again, compared to the cutoff.
Let me explain. So this is pure pheno. Okay, this is non-stringy, right? Okay. So if this point, our minimum here is at 0. At 0, I mean after the quintessence field has rolled to far enough to infinity. Okay. And I have here a positive curvature in all directions, such that I have no trouble with long-range forces due to chi. Okay. Then the situation is that I go somehow up, and then I have to turn over to the saddle. And then the mass determines how high you are up. So if you are willing to have this particle very light, you can have the saddle very low. Now comes a next twist. You can, in fact, have this point a little bit below 0, because quintessence could take us to ADS, just a little bit. Okay? Then this would be a little bit below 0. The mass could be tiny, but still large enough to avoid equivalence principle violation, say. And then you could construct something which is kind of a very flat trajectory going here, with a very flat saddle still below 0, not violating the conjecture. Now, I kind of emotionally, I'm troubled with this, but I'm open-minded. I try to be, so, okay. But logically, you're right. And we noticed it in the paper, I just had no time, sorry.
Are there further questions? If not, then let's thank Arthur again.